If one passes the discharge of a fairly large Ruhmkorff induction coil through a Hittorf vacuum tube, a sufficiently evacuated Leonard or Crookes tube, or a similar apparatus, and if one covers the tube with a rather closely fitting envelope of thin black cardboard, one observes in the completely darkened room that a piece of paper painted with barium platinocyanide lying near the apparatus glows brightly or becomes fluorescent with each discharge. One easily convinces oneself that the cause for the fluorescence emanates from the discharge apparatus and from no other point in the circuit. I observed that the fluorescent screen still glowed brightly behind a bound book of about 1,000 pages. The printer's ink had no noticeable effect. Likewise, fluorescence appeared behind a double pack of whist cards. The eye can hardly detect a single card held between the apparatus and the screen. Also, a single sheet of tin foil is hardly perceptible. Only after several layers have been placed on top of the other does one see the shadow distinctly on the screen. If one holds the hand between the discharge apparatus and the screen, one sees the darker shadow of the bones within the much fainter shadow picture of the hand itself.
We're not really using X-rays here. This is just a studio mock-up. But with those words and describing apparatus fairly similar to this, Wilhelm Röntgen announced his discovery of a new phenomenon, a phenomenon that he called X-rays. It was a discovery that excited tremendous interest, not only from the scientific community, but from the public at large. This was Life magazine's somewhat morbid view of the new discovery. The practical uses of these X-rays in medicine were obvious, and within weeks, surgeons were using them as a very effective diagnostic tool. Equipment like this was in use after the Battle of Omdurman, less than 3 years after the discovery. But what excited the physicists of the day was that here was a new and completely unexplained phenomenon. Just what were these X-rays, and how were they being produced? Well, it was 20 years or more before these questions were fully answered. But before we see how, let's just look at the sort of apparatus that Röntgen was using. Like a lot of discoverers in science, Röntgen's owed something to luck. He was actually studying electrical discharges in a tube like this. He produced a high voltage using this device. It's called an induction coil, and the voltage was passed through these wires to the 2 electrodes in the evacuated tube. Now, the electrode at the bottom here was maintained at a high positive voltage, and that dragged electrons out of the second electrode. They accelerated down the tube, flying straight past the positive electrode, and hit the glass at the end. And it was from this region of the glass at the end of the tube that the mysterious new radiation appeared to emanate. Well, one theory that was put forward was that X-rays might be electromagnetic radiation of very short wavelength. And they had to be of short wavelength because all attempts to diffract them at that time using optical diffraction gratings had been inconclusive. But almost 17 years later, another German physicist called Max von Laue suggested that if the atoms within crystals were as regularly spaced as he thought, then they would act as a 3-dimensional diffraction grating, a grating with perhaps a small enough spacing to diffract the X-rays. Well, within a year of his suggestion, the experiment had been performed, and sure enough, diffraction patterns were observed. This more or less confirmed that X-rays were part of the electromagnetic spectrum, of the same nature as visible light, but with wavelengths about 10,000 times shorter. This new understanding of what X-rays were, and the application of the new techniques of X-ray diffraction, soon gave a boost to the newly emerging quantum theory, a boost that came about from measurements of X-ray spectra.
X-ray spectra were investigated using apparatus like this. Basically, it consists of an evacuated tube with 2 electrodes inside. Now, there's a potential difference of several thousand volts across these electrodes, and that accelerates electrons from one to the other. Well, as Stuart said, in Röntgen's first experiment, the electrons struck the glass wall of his tube. But here, the electrons are aimed directly at a target, which is normally made of a heavy element such as molybdenum or tungsten. When this target is struck by the accelerated electrons, X-rays are given off. Well, the early investigators were particularly interested in 2 questions. First, in what way did the X-ray emission depend on the accelerating voltage? And secondly, in what way did the emission depend on the target? Well, let's have a look at some of the results they found. Along this axis, we've plotted the wavelength of the X-rays in units of nanometers, up to a maximum of 0.24 of a nanometer. And up along this vertical axis, we've plotted the intensity of the X-rays. Well, when the target was molybdenum and when the accelerating voltage was 10,000 volts, this is what they found. It's a continuous spectrum. There's a continuous range of X-ray wavelengths here. Well, we can understand this result qualitatively using some simple ideas based on classical physics. When an electron hits the molybdenum target, it slows down, and because it's a charged particle, it gives off electromagnetic radiation. The kinetic energy of the electron is converted into the energy of the radiation, which in this case is in the X-ray region. Well, now, think what happens when an electron is brought immediately to rest in one collision in the molybdenum target. In this case, all of the electron's kinetic energy is converted into the energy of the radiation. So in this case, the radiation given off will have the highest possible energy. That's to say, the shortest possible wavelength. Now, that's why there's a cutoff in this spectrum. It's these shortest wavelength X-rays that are given off by electrons that were stopped dead in one collision in the molybdenum target. Well, so much for the 10,000 volt spectrum. Let's see what happens when we increase the accelerating voltage to 15,000 volts. Again, a continuous spectrum. Only this time, notice the cutoff wavelength has fallen. Now, that's quite easy to understand. We've increased the accelerating voltage, so if this time an electron stops dead in the target, it will give off X-rays that have an even higher energy. That's to say, they have an even shorter wavelength. No surprises so far then, but let's see what happens if we increase the accelerating voltage yet again. This is the spectrum when the accelerating voltage is 25,000 volts. It has a continuous component again, but this time we have these 2 very remarkable spikes. Now, these show that very intense X-rays are emitted at these 2 particular wavelengths. Now, when the voltage is increased again to, say, 30,000 volts, those spikes stay in exactly the same positions. Well, what can we conclude from all this? Well, since the spike's positions don't change when we alter the accelerating voltage, I think you'll agree that those spikes can have nothing whatever to do with the electrons that are bombarding the target. No, the clue to understanding these spikes comes when we change the target element. For it turns out that each chemical element has its own characteristic X-ray spikes. And for that reason, we say that the spikes in an X-ray spectrum of an element is due to its characteristic X-rays. Now, understanding why these characteristic X-ray lines were in the spectrum was just not possible using the basic ideas of classical physics. Why should every heavy chemical element have these spikes? And yet, as you know, that wasn't the only problem that classical physics couldn't solve.
You should be familiar enough with pictures like this from the main text. It's the visible part of the spectrum from a hydrogen discharge lamp, the part that you'd see using a spectrometer like this. What happens in this instrument is that light from a hydrogen discharge lamp, or any other source that you're interested in, is split up into its different wavelength components by a diffraction grating. The longer the wavelength of the light, the larger the angle through which the light is diffracted. So when you scan this telescope around in this direction, you'll first of all see at a small angle the violet lines. Going to a larger angle, you'll see the blue-green line, and going to a larger wavelength still, you'll see the longer wavelength red light. Each of these coloured lines corresponds to a different wavelength emitted from the hydrogen atom, and other elements have their own quite different characteristic sets of lines. So it seems that there's a very strong similarity between visible spectra and the characteristic X-ray spectra that Graham's just been talking about. In both cases, atoms emit photons with certain well-defined wavelengths, and that means photons with only specific energies, energies that are characteristic of the particular atom. An explanation of these characteristic spectra required greater understanding of matter itself, and this was perhaps the major impetus for scientists to develop a better model of the atom.
This is one of the earliest models of the atom, and it was first put forward by J.J. Thomson. He suggested that the heavy atom consisted of a uniform sphere of positive charge. That's this red cloud, with the negatively charged electrons, they're the green dots, moving around inside it, a bit like mobile plums in a plum pudding. Well, a completely different model was put forward by Ernest Rutherford in an attempt to explain alpha scattering data. In this model, each atom was supposed to contain a positively charged nucleus with electrons moving around it. The nucleus shows up very clearly here, but that's only because we've used our artistic license. If we tried to show the nucleus to scale, it would have had to have been no bigger than a speck of dust. So in reality, the nucleus is very small compared with the size of the atom as a whole. Although these two models allowed some problems in atomic physics to be solved, neither one gave much insight into the problems of understanding visible spectra and characteristic X-ray spectra. But that was to come with a major breakthrough in 1913. This is Bohr's quantum model of the heavy atom. It's based on Rutherford's idea. The electrons are orbiting the nucleus at the core of the atom. And here we've actually shown the orbits of each of the electrons. Now there are some very important differences between this and Rutherford's model. In this, Bohr's model, the electrons moved in these strictly defined circular orbits. There are 2 electrons in orbit very close to the nucleus. There are 8 more at a slightly larger radius, and in this atom there are 4 at this very large radius. Now the point is that these orbits have very well defined radii. They're said to occupy shells in the atom. Now Bohr also suggested that the energy of these electrons could take only certain definite values. This certainly was a very bold assumption. He was suggesting that the electrons occupy definite energy levels. Now in the case of the very simplest atom, the hydrogen atom, which has just 1 electron orbiting the nucleus, Bohr's model can actually be used to calculate these energy levels. And when we do the calculation, we get results like this. We represent the energy levels by these horizontal lines. And you can see how as the energy increases, the energy levels become closer together. Now, the electron can in principle occupy any one of these energy levels, but it will usually occupy only the very lowest one, the so-called ground state. Well, this idea of energy levels was completely new, and it really did revolutionize atomic physics. For the first time, it allowed physicists to understand the very 2 phenomena we've been looking at. That's characteristic X-ray spectra and visible spectra.
In a hydrogen atom, the single electron usually occupies the lowest energy level, the ground state. But the electron can gain energy and be excited into one of the higher energy levels, as happens in the hydrogen discharge lamp. When the electron falls back to lower levels, the energy it loses in each transition is carried away by a single photon. This energy difference is 2.9 eV, and a transition between these 2 levels produces a photon with a wavelength of around 430 nanometers. That corresponds to this violet line in the visible part of the hydrogen spectrum. The other transition involves a much higher energy difference, and so a photon with a shorter wavelength is produced. This time, it's in the ultraviolet region of the spectrum. The 4 lines in the visible part of the spectrum of hydrogen are produced by these 4 transitions. The smallest energy difference gives the red line, while the largest gives the far violet line.
So transitions between these energy levels are responsible for all the lines in hydrogen spectrum, and it's 4 transitions to this energy level that give rise to the spectral lines that we can actually see. The story is much the same for heavier atoms too. If an electron is in an excited state, it will emit visible light if it makes a transition to a lower energy level just a few electron volts below it. But how do we account for those spikes in X-ray spectra that I was pointing at earlier? Remember, those spikes are due to characteristic X-rays, which have wavelengths about 10,000 times smaller than those of visible light. That means for an atomic electron to radiate in the X-ray part of the spectrum, it would have to make a transition between energy levels that were very widely spaced by roughly thousands of electron volts. Now, this can't happen in hydrogen because the energy levels are much too close together. But what about the element molybdenum? Suppose this line represents the lowest energy level of molybdenum. Using the same scale here as we used for the hydrogen energy levels, the next molybdenum energy level would be way up there, beyond the studio lights, and in fact above the Alexandra Palace mast, 2,500 feet up in fact. Well, with spacings of molybdenum's energy levels on this scale, I think you can now see that if an electron were to make a transition from that energy level up there to this one, then the radiation emitted will have a very high energy. In fact, for molybdenum, this radiation is in the X-ray region, and that's why those sharply defined characteristic X-ray lines appear in molybdenum's spectrum.
This is a typical energy level diagram for one of the heavier elements. Only the bottom energy levels are shown, but notice that the energy scale is now marked in keV, thousands of electron volts. Well, what happens in X-ray emission? Normally, each of these energy levels contains its maximum number of electrons. But if the atom is struck by a high energy electron, as it would be in an X-ray tube, one of the electrons may be knocked clean out of the lowest level, and out of the atom altogether. This leaves a vacancy in the ground state. A vacancy which may be filled by an electron making a transition down from a higher energy level, the second level in this case. And because the spacing between these levels is so large, the photon will be in the X-ray part of the spectrum, producing one of the characteristic X-ray lines. So the first step is the ejection of an electron from a low level, and this electron's place is then taken by an electron dropping down from one of the higher levels. In fact, a number of transitions are responsible for X radiation, each of which accounts for one of the element's characteristic X-ray lines.
Well, I think you'll agree Bohr's idea of energy levels has proved to be extremely powerful. It's enabled a clear, unified explanation of both characteristic X-ray spectra and visible spectra. They're both due to transitions between electrons' energy levels. Now, in 1914, the study of X-rays was taken a crucial step further by Henry Moseley, a young English physicist who was once a student of Ernest Rutherford. Now, Moseley's innovation was to use characteristic X-ray spectra to probe beyond the electrons in the atom to the atomic nucleus.
Taking an X-ray spectrum like that of molybdenum, Moseley measured the wavelengths of the strongest characteristic lines. He did the same thing for over 30 other elements. In each case, he measured the wavelength of the most prominent characteristic X-ray lines. He arranged these results in the order in which the elements appeared in the chemist's periodic table. That is, in order of their atomic number. 25 for manganese, 26 for iron, 27 for cobalt, all the way up to 79 for gold. And when he looked at the result, he found that the wavelength of the X-ray lines fell on very regular curves. What's more, when he changed the horizontal axis from wavelength to wavelength to the minus a half, that is, to 1 over the square root of wavelength, he found that each of the curves became a straight line. This demonstrated that there was a clear link between the atomic number and the wavelength of the characteristic X-rays. So what's the significance of these results? At the time of Moseley's experiments, Rutherford had proved that the nucleus of the atom was positively charged. It had also been suggested that this positive charge came in integral multiples of the charge on the hydrogen nucleus. What's more, the integer that determined the charge was thought to be the atomic number, the number which gave the position of the atom in the periodic table. So molybdenum, for example, which was the 42nd element in the periodic table, had atomic number 42, and therefore the suggestion was that it had a nuclear charge 42 times greater than a hydrogen nucleus. The importance of Moseley's experiments was that they provided extremely strong evidence for this idea. Let's use Bohr's model to explain why. The electrons closest to the nucleus, these in the lowest energy levels, are the ones responsible for the characteristic X-ray lines. But the electrostatic force on these innermost electrons is mainly due to the positive charge on the nucleus. Therefore, it's the charge on the nucleus, given by its atomic number, which determines the spacing of the lowest energy levels. So the atomic number must also determine the wavelength of the characteristic X-rays. And that's just what Moseley's results showed. Atomic number determines X-ray wavelength. We haven't gone into the details of the argument, just why these lines should be straight, but Moseley's results certainly did confirm that atomic number is a measure of the charge on the nucleus. It was unfortunate that Moseley didn't live to receive the same recognition for this work that Röntgen and Bohr did. Had he not been killed in action in World War I, there's little doubt that he would have joined the ranks of Physics Nobel Prize winners for this important contribution to our understanding of the atom. It was only 20 years before Moseley published these results that Röntgen discovered X-rays. At the time, nobody had much idea about the structure of atoms, and some respectable scientists didn't even believe that atoms existed. But as you'll see later in this course, even in 1914, the understanding of the atom was very far from being complete. In the next 20 years or so, the work of Schrödinger, Heisenberg and others produced a revolution in the understanding of the atom, a revolution that was at least as dramatic as the changes that had been witnessed in the time between Röntgen's discovery and Moseley's work. But though the new revolution led to the eclipse of the Bohr model, its most important prediction survived, that atomic electrons occupy definite energy levels, and that these energy levels determine the characteristic spectra of the elements. Energy levels had come to stay.